Ready? Okay. So just a reminder to you should have traded papers by now with a classmate, and make sure you bring the paper and the summary along with your peer review of that to class on Monday to turn that in. Today we're going to talk about alcohol oxidation. There's quite a bit to say about alcohol oxidation, so that'll take most of the time. And then we'll talk at the end of chapter 12 about enantioselective epoxidations. This is our first reaction where we're going to form a single enantiomer of a chiral molecule from an achiral precursor. And we're going to use a chiral catalyst to do so. And then we may or may not have time at the end to start chapter 13 and talk about mass spectrometry. If not, that's okay, because it's chapter 13 is our shortest chapter, and it's easy to summarize that on Monday. So at the end of class on Wednesday, we told you that oxidations of alcohols have different outcomes depending on the type of alcohol that we have. Primary alcohols can either be oxidized to give aldehydes or ketones. Secondary alcohols can be, aldehydes or carboxylic acids is what I meant to say. Secondary alcohols can be oxidized to give ketones, and tertiary alcohols cannot be oxidized. So we've drawn here on the board the reagents that are most commonly used for oxidation. And these are chromium-based reagents. Chromium is a very good oxidant, so we'll explain why in a moment. But we have two types of chromium reagents. We have our water-soluble and organic insoluble chromium reagents. These are all purely inorganic molecules. They dissolve in water. And when we use one of these water-soluble reagents in an oxidation, we have to use sulfuric acid in conjunction with those reagents. And then we have PCC, or pyridinium chlorochromate, and that, because the cation here, the pyridinium ion, which is the conjugate acid of pyridine, is an organic molecule. So that makes this salt soluble in organic solvents. So when we perform an oxidation using PCC, we use dichloromethane as our solvent. Okay? So when we're oxidizing a secondary alcohol, it doesn't matter which of our reagents we use, we have the same outcome. So we could use dichromate, sulfuric acid, and water. That would give us our ketone, acetone in this particular case, or we could use PCC with dichloromethane as the solvent, and we would have the same outcome, the same product of that oxidation. Okay? So before we show you the mechanism of oxidation, we'll just show you a general outline of what happens when we oxidize an alcohol. So we take our alcohol, and in the first part of our mechanism, we convert the alcohol into a good leaving group. Okay? Or I should say, we attach a good leaving group to our oxygen of our alcohol. In the past, we have actually converted an alcohol into a good leaving group. And as you'll see in the key step of this oxidation, attaching a leaving group to an oxygen is different than converting an alcohol into a leaving group. When we convert an alcohol into a leaving group, the oxygen leaves as part of the leaving group. But in this case, what happens is we use a base to deprotonate the alpha hydrogen. We're going to use the electrons in that carbon-hydrogen bond that are breaking to form a carbon-oxygen double bond, and then our leaving group is going to depart. Okay? So the oxidation of alcohols has an elimination as the key step, and it's a little different from eliminations we've seen before because we're forming a carbon-oxygen bond as opposed to a carbon-carbon bond. That's due to the fact that the oxygen of the alcohol is not part of the leaving group. We have attached a leaving group to that oxygen, allowing us to perform this type of elimination. Any questions? Yes, Noah? Yeah, you can't, if you had a hydrogen here, then you'd have H minus as your leaving group if you were doing this. Okay, we don't use H minus as a leaving group. Enzymes can do it, as we'll see later on in class, but chemists using flasks cannot do it. We can't do it without using enzymes. So we have to attach a leaving group to this oxygen in order to perform these oxidations in a flask in a lab. So let's show you how that is done specifically. Let's draw the mechanism for the oxidation of an alcohol. And we'll just use R groups to make it a generic secondary alcohol. Okay. So we'll also draw the mechanism with chromium trioxide, CrO3. And we can do this regardless of which of the oxidants we're actually using in the reaction. Because these dichromate reagents, when you dissolve them in solution, they're going to dissociate and give you something that's either CrO3 or something very similar to it. And the same thing applies to the pyridinium chlorochromate. That gives you something similar or functionally equivalent to chromium trioxide. So regardless of the reagent, we're going to use chromium trioxide to draw the mechanism. So chromium trioxide has a transition metal here, which has a very, very low electronegativity, and it is bonded to more electronegative atoms through 6 bonds. Okay, 6 bonds to more electronegative atoms. That makes this chromium quite electrophilic. If we're counting oxidation states, it's chromium 6. So a very high oxidation state. It wants to be reduced. It wants electrons. It's very electrophilic because of the high partial positive charge due to these 6 bonds to more electronegative atoms. So this allows us to attack that chromium with a weakly nucleophilic alcohol. And as we do so, we can break one of the carbon or one of the chromium oxygen pi bonds and push those electrons up onto the oxygen. Okay, so that's going to give us a species. It looks like this. Okay. So this is the intermediate we get after water or after an alcohol attacks chromium trioxide. If you look at the mechanism in the book, it just has these magic words, proton transfer over an arrow, and then draws an intermediate without showing any curved arrows. We're not going to do that. We're actually going to show you the individual proton transfer steps because it's important to understand what's going on. So we have acid in the reaction mixture. So that H3O plus, that acid can protonate the negatively charged oxygen on the chromium. Okay. So if we do that, if we protonate this oxygen, that gives us this intermediate shown here. And then we can react that with water. We also have water present. We formed water in this step right here. And so the water can deprotonate that intermediate and give us this species. Okay? So you might wonder, couldn't we just use this negatively charged oxygen to deprotonate the positively charged oxygen? Couldn't we just perform an intramolecular proton transfer? Well, we could, but that would involve a four-membered cyclic transition state. We have seen one of those before. We've seen it in the hydroboration reaction, so that's possible. But we know that four-membered rings are strained. They have angle strain. And so that transition state would be somewhat elevated in energy. And we've also taught you that proton transfers between two heteroatoms are the fastest steps that we have in organic reactions. So since we have H3O plus in the solution, there's a very rapid proton transfer from H3O plus to this oxygen, and then a very rapid proton transfer between water and this oxygen. And those two steps are faster than making a four-membered transition state that's going to be relatively high in energy. So it's much better to draw the mechanism of this reaction in this fashion with two consecutive intramolecular proton transfer steps. Any questions? Okay, Parker. Yes. Yes. We haven't gotten to the part where the chromium is satisfied by having more electrons yet. Yes. The weak nucleophile can attack the chromium because that chromium has a high partial positive charge. But we have yet to reduce the chromium, but that's coming in our next step. So now that we have this intermediate, we can use another water molecule as a base, and it can deprotonate this alpha hydrogen, and then we can use the carbon hydrogen sigma electrons to make a carbon oxygen pi bond, and then we can break the chromium oxygen sigma bond and push those electrons onto the chromium, and then we can break another one of our chromium oxygen pi bonds in the process. Okay? So this is an elimination step. We've got an extra arrow because we're pushing electrons from the chromium onto the oxygen here. And so that is going to give us our ketone. Okay, our ketone comes there. Then we have a chromium byproduct. Which looks like this. This ion, I'm not great with my inorganic nomenclature, but I believe that's referred to as chromite. And then we also produce H3O plus in this step as well. Okay. So this is our oxidation step. Our intermediate, the intermediate derived from the alcohol is losing the electrons in this sigma bond. Those electrons are both going to the chromium, so the chromium is getting reduced, and the alcohol is getting oxidized to give us the ketone. And if we look at our chromium byproduct, we now see it only has 4 bonds to more electronegative atoms, and there's a lone pair on the chromium, so we've reduced the chromium. And that driving force, the desire of the chromium to be at a lower oxidation state, is what allows us to perform an E2 reaction, to perform an elimination step using a weak base. Right? It's rare to see E2 reactions with weak bases. The driving force is the reduction of the chromium in this particular case. Any questions on that mechanism? Tucker? Okay. Okay, yeah, so why do we not deprotonate here, you're saying? Yeah, so that's part of it. Another part of it is you could conceivably deprotonate that, but nothing else would happen, and that proton transfer would be reversible. So you probably have deprotonation events happening there, but because it's a dead end, then it's just going to reverse back. And then when we do this, this is irreversible and gives us the product. Okay? Other questions? Okay, so that's what happens when we oxidize a secondary alcohol. Now let's look at what happens when we oxidize a primary alcohol. Here, we're going to have two different outcomes depending on the oxidizing agents that we use. If we use PCC with dichloromethane as our solvent, we're going to obtain an aldehyde product. But if we use any of our water-soluble reagents, let's just use chromium trioxide, sulfuric acid, and water, we're going to obtain a carboxylic acid. Okay? Now, the mechanism of aldehyde formation from a primary alcohol is identical to the mechanism of ketone formation from a secondary alcohol. So we're not going to draw that mechanism. The only difference is that when you're forming an aldehyde, you don't have H3O plus and water. When you need an acid, you would use the pyridinium cation. That's acidic enough to function as the acid in this mechanism. And when you need a base, you would just use the pyridine, the conjugate base of the pyridinium cation. Okay? So those would function as the acid and base in the mechanism for forming this aldehyde from this primary alcohol. The mechanism of forming a carboxylic acid is more complicated. It actually involves two oxidation events because the carboxylic acid is two oxidation states higher than the alcohol. Okay, so it has two oxidation events and another part to it, so it's a three-part mechanism. And so it'll seem daunting if you think of it all together, but if we break it up into the three parts, it should be more straightforward to understand. Okay, so part one, we're not going to draw out the mechanism for part one because we have seen it before. We take our primary alcohol, we react it with a chromium-6 oxidant, and that chromium-6 oxidant generates, an aldehyde, okay? By the same four steps that we showed you here: alcohol attacking the chromium, two proton transfers, deprotonation of one of these hydrogens, elimination to give the aldehyde. Okay, so same four steps that we drew for you on the upper board. Okay. Part two of the mechanism is going to be new, but it's going to be comparable to things that we've seen before. So in part two of the mechanism, we're going to form an intermediate known as a hydrate. So we're going to start with our aldehyde. Our aldehyde is the product of the first part of the mechanism. And we're going to react that aldehyde with H3O plus. So if we're going to protonate an aldehyde, which atom of the aldehyde do you think we're going to protonate? The oxygen. We have lone pairs on the oxygen. The oxygen is Lewis basic, so we protonate the oxygen. Okay? And this is reversible. We'll talk about that in a moment as well, but we'll use equilibrium arrows to draw this mechanism. Okay? And we've actually seen a step like this before when we were drawing the actual mechanism of the mercury-promoted hydration of alkynes. We formed a carbonyl and we protonated that carbonyl at one point in the mechanism. So we've seen protonations of carbonyls before. What that does is make our carbonyl functional group very electrophilic. It's positively charged, so it's electrophilic enough that a weak nucleophile such as water is able to attack. But our water is not going to attack our positively charged oxygen. Instead, it will attack the carbonyl carbon so that we can push the pi electrons onto the positively charged oxygen. Okay? This is the sort of thing we're going to see time and time again in Chem 352 when we talk about the chemistry of carbonyl groups. So we'll see protonation of a carbonyl, attack of water or another weak nucleophile onto the carbon. Okay, so that's going to give us an intermediate looking like this, a tetrahedral intermediate. So we've changed the hybridization of this carbon from sp2 to sp3 by virtue of that attack. And so now we can use another equivalent of our water to deprotonate. And that gives us a diol, but a special type of diol where we have both OH groups on the same carbon. That's a geminal diol. It's also known as a hydrate. Because if you look at the aldehyde and you look at the hydrate, you can see the difference between them as we've added an equivalent of water to the aldehyde. So that's why this is referred to as a hydrate. And we're also generating H3O plus in that third step. Okay? So you'll notice these are the same three steps in the acid-promoted hydration of an alkene, except we protonate an alkene instead of protonating a carbonyl. But when we do the acid-promoted hydration of an alkene, we protonate, water attacks, and then we deprotonate the oxygen of the water to get the final product. So it's the same three steps. It's just applied to a carbon-oxygen double bond as opposed to a carbon-carbon double bond. Any questions about this mechanism? So I've drawn equilibrium arrows for you. And in the vast majority of cases, this equilibrium is unfavorable. The aldehyde is usually more stable than the hydrate. So you're typically only going to obtain 1% or less of the hydrate. But that's all we need because the third part of the mechanism is going to be irreversible. Okay? So in the third part of the mechanism, we're going to take our hydrate and we're going to recognize that our hydrate bears some resemblance to our original alcohol in that we have a hydrogen atom on the carbon that bears the oxygens. So I should write part 3 here. So when our hydrate reacts with another molecule of chromium trioxide, then one of our equivalent alcohols on the hydrate is going to attack the chromium in the same way that we saw in the first step of part 1. And I'm not going to draw the intermediates out because I've drawn them before. We're just going to cut to the chase to get to the key intermediate that we'll have. Which will look like this. Okay. So once we get to this intermediate, then our water will deprotonate and will generate our carboxylic acid, our chromium 4 byproduct. I'm not going to draw it out this time. It's drawn out on the upper board, and our H3O plus. Okay. So 3 parts to the mechanism. 2 parts have the exact same 4 steps, part 1 and part 3. Those are the oxidation parts, where we oxidize from a primary alcohol to an aldehyde, and then from a hydrate to a carboxylic acid. The part in the middle is where we convert the aldehyde into the hydrate. And even though the equilibrium for part 2 is unfavorable, part 3 is irreversible. As we form hydrate, it gets converted irreversibly into carboxylic acid, and according to Le Chatelier's principle, some of the aldehyde will react to give the hydrate. So we can drive the reaction through an unfavorable equilibrium by having an irreversible process after that equilibrium. Any questions? Okay, so I have a question for you then. Based on what we've talked about so far, you should be able to tell me why the use of PCC as an oxidant stops at the aldehyde, stops at part 1 of the reaction, and does not proceed further to give the carboxylic acid. Yes, please. Very good. There is no water present. PCC dissolves in dichloromethane. So we can run the reaction in the absence of water. Water is required to make the hydrate. So if we have no water, we have no hydrate. So that's why it stops at the aldehyde. Okay? So a very simple, very effective way of producing the aldehyde. Use an oxidant that we can avoid water with. If we want the carboxylic acid, then we use our oxidants that dissolve in water so that we have water present to produce the hydrate. Okay, so a practical application of these chromium oxidations was in early alcohol testing devices or breathalyzers. Okay, so the chromium, we start with chromium 6, and at the end of the mechanism I've drawn for you, we end up with chromium 4. But the chromium byproduct undergoes chemistry we don't talk about because it's after the oxidation of the alcohol. It doesn't play a role in the oxidation of the alcohol, but eventually we end up with chromium 3 as the final chromium byproduct. The chromium 4 undergoes additional inorganic chemistry to give chromium 3. Now that's significant because chromium 3 is green, and the chromium 6 species are reddish orange. And so as you oxidize an alcohol to a carboxylic acid, your reddish orange dichromate is going to be converted into a green chromium 3 byproduct. So if you have a tube that contains dichromate and you breathe into that tube and your breath has alcohol in it, that alcohol is going to get oxidized and the chromium is going to change colors as it gets converted from the chromium 6 ultimately into chromium 3. And if you have more alcohol in your breath, the green is going to travel further down the tube, and you just count the number of lines to where the green ends, and that would give you an indication of how much alcohol was in the individual's breath. Okay? So we're going to test this out, not with our breath, but with some ethanol that we have here in a graduated cylinder. And so we have 2 test tubes here. I'm going to use the gloves I didn't use last time. And we're going to put ethanol in one of them. And then this oxidation, to speed it up a little bit, we have a warm water bath here that's going to allow us in a few minutes to see the color change. So let me get this off here. Put my safety glasses on. Okay, so we're going to pour our ethanol in. Mix that up. Put that into our water bath. And then as a control, just so that you can see the color change more clearly, we have the dichromate that we didn't add any ethanol to, and we're going to put that in the water bath as well. Okay, and it'll take a few minutes to change colors, so we'll come back to that shortly. Chromium is toxic, so fortunately we don't use this method anymore for breathalyzers. It's been replaced by spectroscopy methods of detecting ethanol, so we don't have to use toxic chemicals in the process. But originally, the early breathalyzers that came out many years ago did use this chemistry. Okay. All right. So based on what we've learned with oxidation of alcohols, we should be ready to practice. So let's go ahead and get out our iClickers. We have 3 iClicker questions on the slide. And so we're starting with number 1. We have the same answers, the same 5 answers for each question. You're just supposed to select the type of compound that is produced by each of these 3 reactions. So go ahead and talk to your neighbors and answer number 1. And then when we're done with that, we'll move on to number 2. All right. Let's see. Okay. Let's see if we have all of our answers. Give you a few seconds. Okay, we'll go ahead and close off our first one and open up the second one. Okay. Sounds like we're done. Go ahead and stop this one. And now we're on to the third one. Okay, we'll give you a few more seconds. All right, I guess we'll go ahead and stop that. Okay, secondary alcohols. What do we obtain when we oxidize secondary alcohols with any of our oxidants? Ketones, okay. Primary alcohols and PCC, what's the product? Aldehyde, good. What would we use if we wanted the carboxylic acid? Chromium trioxide or dichromate, either of those, okay. And what happens when we attempt to oxidize a tertiary alcohol? Nothing. There's no hydrogen attached to this carbon, so there's no way to oxidize it. So nothing will happen. Okay, very good. All right, let's take a look and see how our breathalyzer reaction is going. And we see we have a bluish green solution from the ethanol being oxidized, the chromium being reduced, and then the one where we didn't add the ethanol, the color has not changed, so it's not the heating that caused this. It was in fact, the oxidation. Okay, so this is how they originally detected alcohol in people's breath. But as I mentioned, with the chromium being toxic, this method has been replaced by more environmentally friendly methods. And that leads us into a subject known as green chemistry. Green chemistry refers to a more environmentally friendly method of performing organic synthesis. So there's a lot of different aspects of green chemistry. If we're replacing toxic or hazardous reagents with safer reagents, that's one form of green chemistry. And your book spends some time talking about some more environmentally friendly methods of performing these oxidations. So we're not going to go into the specifics. There are a lot of safer reagents and less toxic reagents for oxidizing alcohols that are actually used in the lab. We do return to the chromium reagents in cases where those ones don't work. We teach you the mechanisms of the chromium-based oxidations because those are a little easier to understand than the mechanisms of some of the more modern oxidants. Other aspects of green chemistry would be reducing the amount of solvent that you use. Typically, you have to dispose of the solvent after a reaction, or other types of waste, byproducts that are formed. Any way that you limit that, that's going to be better for the environment. So any way of making chemistry more environmentally friendly is referred to as green chemistry, and that's a very popular buzzword these days, one that you'll hear frequently, and so it's important to understand what it means. But we're going to focus just on the general concept and not specific aspects of green chemistry in here. But the next thing we're going to talk about is how oxidations are performed in biology, how they happen inside of living systems. Our bodies perform oxidations quite frequently. The hope is that none of your bodies are performing this particular oxidation, but it is one that is performed in the bodies of many college students on many other college campuses. If we take ethanol, if a human ingests ethanol, that ethanol is going to react with a cofactor. That cofactor is abbreviated as NAD+. That stands for nicotinamide adenine dinucleotide. It's a long name and an even longer molecule. So we'll just abbreviate it as NAD+. And that cofactor is going to be at the active site of an enzyme called alcohol dehydrogenase. Okay? And this is going to be a reversible process because this enzyme can catalyze both oxidations and reductions. The product would be an aldehyde, and then the reduced form of the cofactor is NADH. And then the aldehyde can also react with NAD+ in the active site of the enzyme, which I will abbreviate now. And that gives acetic acid and NADH. So your body metabolizes ethanol by converting it into acetic acid. Then it gets excreted. So if you ingest more alcohol than your body can process, then you start to get a buildup of the aldehyde, the acid aldehyde. And the acid aldehyde is what provides the symptoms of the hangover. So in people who drink too much and they have a hangover the next day, they have a headache, they don't feel good, that's due to having, that's the effects of having this aldehyde in your system, okay? But then that goes away, that's temporary, because then your body will eventually process that and convert it into the acetic acid. But methanol is toxic. Of course, ethanol is toxic if you drink too much of it, but methanol is really, really toxic, okay? And we'll see why as we draw out the intermediates and products that are formed. If we oxidize methanol, we obtain this aldehyde. Does anybody know what that aldehyde is called? That is called formaldehyde. So if you've heard of formaldehyde, you know that formaldehyde is toxic. Okay, so that's problem number one. You produce a toxic aldehyde when your body oxidizes methanol. Okay, and then the oxidation of the formaldehyde generates the 1-carbon carboxylic acid. That's called formic acid. And formic acid is about 10 times more acidic than acetic acid. And so when you generate formic acid, then your blood pH drops, and that causes toxicity. So it makes your blood too acidic. So 2 reasons why you should never ingest methanol. That's why in many labs they spike ethanol with methanol so that the students will not drink the ethanol or try to mix it in and distill their own beverages in the lab. That has happened from time to time at other universities. People distill gin or other sorts of things in the lab with ethanol. But the way to de-incentivize that is to spike the ethanol with methanol. Because then if you were to drink that, you would, at a minimum, go blind. And then the worst thing that would happen is you would die. Okay? So the mechanism of this, yeah, question. I don't really know that methanol is used much outside of lab settings. I can't think of any instances. But it's not, you would have to ingest it. We use it in the lab all the time, and its vapor pressure is such that you're not inhaling enough to cause yourself damage. You would actually have to ingest it for it to be toxic, fortunately. So the mechanism of this oxidation is very different from the mechanism of oxidation in a flask. So what happens, we'll come over here, the NAD plus, as I told you, is a very large molecule, but most of it is just designed to form non-covalent interactions with polar functional groups in the active site of the enzyme. So you have a lot of hydrogen bonds between this part of the molecule and the active site of the enzyme to put it in the right location. It's this part right over here, the 6-membered ring with the positively charged nitrogen, that is functioning as the oxidizing agent. So what happens is your alcohol gets to a certain spot in the active site, and it's going to be held there also by hydrogen bonding to the side chains of the amino acids in the active site. A base in the enzyme can deprotonate the OH, and then we can form our pi bond using the oxygen-hydrogen sigma bonds. And then we can have H- or hydride as a leaving group. Okay, now that's pretty crazy. I told you earlier we can never do that in a flask. H- is an incredibly strong base. But what happens in the active site of the enzyme is you don't have H- floating around. You have the NAD plus held in place by hydrogen bonding right next to the alcohol, so that this H- just hops from one molecule to the other. It's not really floating around in solution. So Because of the very close proximity that we have of the cofactor and the alcohol in the active site, in nature, we're able to perform this oxidation that would be very, very, very difficult to perform in a flask. And that gives us our aldehyde. It gives us the reduced form of our cofactor and the conjugate acid of our base. And this is reversible. When we talk about reductions next semester, we'll see how NADH can actually function as a reducing agent. But for now, we're just learning the oxidation. Any questions? All right, so up until now, we've told you that when you form a chiral product from achiral starting materials, that you generate a racemic mixture. So now we're going to tell you how we can form a single enantiomer, or at least a major enantiomer and a minor enantiomer, from an achiral starting material. And that's using a reaction that we'll call the Sharpless asymmetric epoxidation. And the asymmetric is referring to the fact that we're not getting a one-to-one mixture of enantiomers, that we're getting a major enantiomer and a minor enantiomer. So we could call that an asymmetric reaction, since it's not giving us a one-to-one mixture. We can also call it an enantioselective reaction. Okay. This reaction is named after Professor Barry Sharpless. He was a professor, he still is actually a professor. He's in his 80s now, but he was at MIT, and then he was at Stanford, and then he was at Scripps in San Diego, where I got my PhD. And so I had a class from him. He's the one who told me the story I told you last time about Bryant Rossiter and the Gypsy Moths, because Bryant Rossiter was a graduate student working for Barry Sharpless at Stanford and helped him discover this reaction. Okay, and Sharpless ended up getting the 2001 Nobel Prize as a result of this and another asymmetric or enantioselective reaction that he discovered. So if we look here on this slide, we can see a couple of examples of a Sharpless asymmetric epoxidation. What you see they have in common is the starting materials are both allylic alcohols. We've learned the term allylic referring to an sp3 carbon that is bonded to an sp2 carbon of an alkene. So for the Sharpless enantioselective or asymmetric epoxidation to work, we have to have an allylic alcohol. Okay, our alkene has to be an allylic alcohol. The reason is we need this OH group to attach, to bind to the chiral catalyst. Okay, if it doesn't have the OH group, it's not going to get attached to the chiral catalyst. So this is tert-butyl hydroperoxide. It's an alkyl hydroperoxide. It's one of our oxidants that has an oxygen-oxygen bond. That's our stoichiometric oxidant in this reaction. Our catalyst is this titanium-4 species. And the thing that's called DET is a chiral diol. And that chiral diol attaches itself to the titanium. Titanium is what's known as an oxophilic metal. Alcohols really bond to it strongly. And so your catalyst is going to be a combination of this chiral alcohol as a single enantiomer. You can have either enantiomer. One of them is a byproduct of winemaking, occurs in grapes. The other one is not part of that, but is still readily available. Okay, so you can have either enantiomer, the one that rotates plane polarized light in the clockwise direction, or the one that rotates plane polarized light in the counterclockwise direction. Okay, so these reactions give a major enantiomer, usually in greater than 90% enantiomeric excess. Usually you have 95:5 or better ratios forming the major enantiomer. The book spends a lot of time focusing on a mnemonic device that tells you if you use the plus enantiomer, it'll epoxidize from one face. If you use the minor enantiomer, it epoxidizes from the other face. I don't have that mnemonic device memorized, and so neither should you. You should just completely ignore that. If you were ever running one of those reactions in the lab, you would double and triple check to make sure you were using the right one. So even if you memorized the mnemonic, it wouldn't matter. You'd check it anyway. So it's useless to memorize. So don't focus on that. We're not going to learn the mechanism because it's complicated. But what happens generally is the chiral diol, the allylic alcohol, and the oxidant all get attached to the titanium. And then one of the oxygens from the hydroperoxide gets transferred to the alkene in a similar way to the MCPBA mechanism. But what we will talk about, just in the last couple minutes here, is how it's possible for us to obtain a major enantiomer and a minor enantiomer from a reaction. So I'm going to draw an energy diagram for you. We'll have a starting material, and we'll have a pathway that leads to our major enantiomer. And then we're going to have another pathway that's going to lead to our minor enantiomer. Okay? Our two enantiomers are equivalent in energy. So if we are relying on thermodynamics, there's no way to obtain anything other than a one-to-one mixture of the enantiomers. Okay? It's impossible, if we're relying on thermodynamics, to get a non-racemic mixture. It's always going to be one-to-one. So what we have to do is use kinetics. We have to make it so that the pathway leading to the major enantiomer is faster, has a lower activation energy, than the pathway leading to the minor enantiomer. If we can form one enantiomer faster than another, and there's no equilibrium between them, we can end up with a major enantiomer and a minor enantiomer. So I've drawn that for you here. The transition state leading to the minor enantiomer is higher in energy than the transition state leading to the major enantiomer. So how can we make one transition state higher in energy than the other? If we have a chiral catalyst, and we have a single enantiomer of that chiral catalyst, at the transition state, we have a partial epoxide. Okay? If we had no chiral catalyst, the transition states leading to each enantiomer would be mirror images of each other. They would be enantiomeric transition states. They'd have the same energy. But if you have a chiral catalyst involved in the transition state and a single enantiomer of that catalyst, now those transition states are diastereomers of each other. Okay? So with a chiral catalyst, these two transition states are diastereomers. Diastereomers are not equivalent in energy. We can have one more stable than another. We've seen this with alkenes. Cis and trans alkenes are diastereomers of each other, and they have different energies. So our different transition states that are now diastereomers of each other because of the effect of the chiral catalyst have differences in energy. And so the reaction proceeds predominantly through the lower energy pathway, giving us a major enantiomer. Any questions? Okay, so we ran out of time to do mass spectrometry, but like I said, we'll have plenty of time on Monday. This is an important topic to digest, much more important than what the book mentions about asymmetric epoxidation. So make sure you've got that down in your notes, and make sure to do the peer review and turn that in on Monday.